Okay, so today's lesson is lesson number 6 on frictional forces. So I'm going to teach you about two different kinds of frictional forces that we're going to be learning in grade 11. One is static friction, and the other one is kinetic friction. So first, friction. Friction is a force which is always going to be parallel to the surface between two objects. This is similar to or not similar to, but the exact opposite of the normal force, because the normal force is always perpendicular. Okay? So, for example, if I took my hands and put them together like this, and I push them together, well, there's a normal force out in this way. But then if I start sliding them like this, there's frictional forces parallel to that direction. And there's two types of frictional forces. One is static friction. The other is kinetic friction. So static friction is there because it sort of prevents you from getting an object to start to move. So let's go with my fridge example. If you're trying to push a fridge across the floor, you can be pushing on it with a certain force and it's not moving at all. If it's not moving at all, there must be some force opposing your applied force. It's static friction. Now once you sort of overcome static friction. So if you push hard enough that you overcome static friction, well, then the fridge starts moving. It still doesn't move very easily, though. There's still a force opposing that motion. Right? And once something is sliding over something else, like the fridge sliding over the surface of the floor, now that's called kinetic friction. And I'm sure you've all noticed that if you're trying to push something heavy, it's a lot harder to get it to start to move than it is to keep it moving. So I want to look at this graph down here. Let me zoom in. Zoom in a lot here. Here we go. So this graph shows us on the y-axis, the vertical axis, we have the force of friction, and here you have time. So let's say you were trying to push something. Right? Now, as you push it, right, if you increase your force over time, let's say you're increasing your force over time, right, it's not moving yet, but the force that is opposing you is getting stronger and stronger. And the harder you push against it, the stronger that opposing force is until you reach a peak. This we call the maximum value of static friction. Okay, all of this is static friction. Here, here, here. That whole area is static friction because our fridge is not moving yet across the floor. But that's the maximum value it can go. So once you apply a force greater than that, then what happens is it drops and you get kinetic friction. It's not going to be perfect in the real world because there might be like little bumps or something. The surface might not be perfectly smooth, right? But it seems like it is a pretty constant value, which is what we're going to go with in grade 11 physics. So we have some maximum static friction that we have to overcome to get an object to start moving. And then once it's moving, no matter how hard we push it, there's a constant kinetic friction opposing us. All right, then, let's look at the factors that can affect friction. So I'm zooming out here. So friction can be affected by two different things. Now, we talked the other day that whether or not something is heavy doesn't affect how hard it is to push it horizontally. Now, that was ignoring friction. What if we don't ignore friction? Well, in this case, sure, gravity is going to push our fridge, we'll just stick with the fridge example, push the fridge down towards the ground, and it's going to make that fridge almost stick to the ground a bit. The heavier the fridge, the more it's going to stick to the ground. But, right, gravity, it doesn't directly affect friction. Because let's say you have a friend that decided to come and help you move your fridge. But instead of pushing your fridge across the floor with you, your friend pushes down on the fridge. Well, now it becomes harder for you to push. Force of gravity on the fridge hasn't changed, but what has changed is that normal force. Because if you have gravity pushing it down and your friend pushing it down, the normal force must counter both of those forces. And so friction is directly proportional to the normal force. So you can see I have two equations here, one for kinetic friction and one for static friction. And they are both equal to some constant, which I will talk about in a moment, multiplied by the normal force. Now, in a sense, it makes sense. The normal force is your contact force. So if you're trying to move something across the surface of something else, how hard they're pushing against each other should affect that. I mean, you can go back with your hand example again. If I lightly put my hands across each other, it's easy to do this. But if you try to push them into each other as hard as you can and then move it vertically, it becomes a lot harder. All right, well, what's this other symbol here, this constant? Well, they're called the coefficients of friction. This one, the coefficient of kinetic friction, for kinetic friction, and this one, the coefficient of static friction. So the other thing that affects frictional force is what those two materials actually are. Right? You can imagine, say, taking, take 2 blocks of ice and put them together and then try to slide them, compared to 2 pieces of rubber from tires and then try to slide them. Okay, obviously, you can imagine a little thought experiment. The rubber would be a lot harder than the ice. Right? It's like trying to walk on ice compared to trying to walk on pavement, for example. Which one would you be more likely to slip on? Well, it would be the ice, even though the normal force on you in both situations is the same. And so that's where these coefficients come from. Now I have a chart here. You have a similar one in your textbook. Okay, but this chart shows different values for the coefficient of static friction and the coefficient of kinetic friction. Notice that the coefficient of static friction is always greater than the coefficient of kinetic friction. This is what leads us to this graph here, that the maximum value of static friction is greater than that of kinetic friction. Okay, you do not need to memorize any of these values. Okay, if I give you something on a test, then you would just simply look up the chart. I would actually give you a chart that you would look it up on. So for example, rubber tire on dry asphalt. So the value, the coefficient of static friction, which is mu s, that's the Greek symbol mu, it's like the letter U with a tail on this one, is 1.2. Now the coefficients, so they don't have any units, they're dimensionless. So you don't need to worry about the units. And rubber tire on dry asphalt, the kinetic friction is 0.8. Then you notice that if the road is wet, that value drops, which is why it's so much more dangerous to be driving on a wet road, or even worse, rubber tire on ice, right, in the winter. Now it's extremely small, right? So even more dangerous, right? You can slip. All right, so something else I want to mention about these equations, you'll notice that I didn't put on vector signs for the forces. That wasn't a mistake. There should not be vector signs on that. And you can see if there were, there's something seriously wrong, because the normal force is always perpendicular to the surface in contact, and friction is always parallel to the surface in contact. So these two vectors are at 90 degrees to each other, and you're only multiplying one by just some scalar quantity. If there were vectors, that equation wouldn't be true. This is simply a magnitude equation. All right, so don't start throwing in negatives because one direction is backwards or anything like that. Okay, you can ignore direction for these equations. Okay, but later when we start looking at the net force, then we will apply a direction to friction because friction does have a direction. So it is a vector, but this equation is not a vector equation. Okay, so let's start with our first example problem. This one says a piano is to be slid across the floor. Oh, stepping up from a fridge now. It has a mass of 450 kilograms. Calculate the normal force supporting the piano. All right, so if we draw a free body diagram, right now the normal force just sitting on the floor is going to have the force of gravity acting on it, and it's going to have the normal force acting on it. Now, since it's just sitting there and it's not moving, that normal force must be equal and opposite to gravity. It's not true in every case, right? For example, if our friend was pushing down on it, or if the piano was on a ramp, right, then it wouldn't be true. But just on a flat surface, sitting there on its own, those are the only two forces on it. It's not moving, so they must be in equilibrium. Put another way, if you like, you can say that the net force, since the piano is not moving, must be equal to 0. Newton's second law says net force equals to mass times acceleration, but if it's not moving, acceleration is 0. So that all equals 0. And then we can choose our coordinate. So we like saying up to be positive, so we'll stick with that. If up is positive, then you can see the normal force minus the gravitational force, because gravity is down, equals 0. Rearranging, you get exactly what we intuitively thought. Normal force, or the magnitude of it anyways, is equal to the force of gravity. So we can calculate that normal force then by calculating the force of gravity, which is mass times their gravitational field strength. And in this question, 450 kilograms times 9.81 newtons per kilogram. And that gives us a normal force of 4,415. Now that's not to the correct significant digits. I'm adding one additional digit just because I'm going to use this in parts B and C. So what is part B? Part B says the coefficient of static friction between the floor and the piano is 0.35. So that's this, that mu s, coefficient of static friction, 0.35. Calculate the minimum amount of force needed to get to the piano to move. Now this is important. This goes back to our graph. So let me look at this graph again. If I could just ask you to calculate static friction, you could calculate any value between just above 0 and just below the maximum value before it starts to move. Okay, but you'll notice all the questions they ask you regarding static friction ask you for that maximum value of static friction right before it starts to move. So we're going to calculate that with our equation. Let me zoom in again. This is part B. Our equation, the force of static friction equals the coefficient of static friction multiplied by our normal force. Right, so we have 0.35, which has no units, multiplied by the normal force, and we get the value, or the magnitude, for static friction as 1545. All right, so that means you would have to apply a force, an applied force of 1,545 newtons to get it to start to move. Now part C says once the piano is moving, a horizontal force of 1100 newtons is necessary to keep it moving at a constant velocity. Okay, now that's important. Let's look at our new free body diagram. So here's our new free body diagram. We still have force of gravity. We have the normal force. Now we have an applied force. And of course, since it's moving, we no longer have static friction. We have kinetic friction, and kinetic friction always opposes motion. So it is back here. Now it says it's moving with a constant velocity, and that's important. It's important again because that means that the net force would be 0. This is no different than in the beginning where the piano was just at rest and wasn't moving. Your net force is 0 because there's no acceleration. In this case, the piano is moving at a constant velocity. If your velocity is constant and not changing, there's no acceleration. It's the same problem. So that means if you look at our vertical component, you can see that the normal is still equal and opposite to gravity. It must be for them to add to 0. But now we can see in our horizontal component, the applied force must also be equal and opposite to kinetic friction. And we can solve for that here. Now, Newton's second law, when you find net force, you would add every single force acting on it. But we can be specific and say the net force in X, or in our horizontal component, where we will make to the right to be our positive X direction. And just like when we did projectile motion, we can completely separate the motion horizontally with the motion vertically. We can do that with Newton's second law as well. We can completely separate horizontal and vertical forces and apply Newton's second law to each. So in this case, you have the applied force minus, so kinetic friction is negative, so because it's we chose the right to be positive, so minus kinetic friction equals 0. Now it says the applied force necessary to keep it moving at constant velocity is 1100 newtons, and we need to solve for that coefficient of kinetic friction. So we know the applied force. So if we rearrange this equation, we get Fk equals Fa. But we're not trying to solve for Fk, we're trying to solve for the coefficient. Now we have an equation for Fk. It is mu k Fn. So mu k Fn equals Fa. Looks like a triangle. There we go. All right, so here's what we're trying to solve for, mu k. So mu k then equals, so divide both sides by the normal force. It's the applied force divided by the normal force. So our applied force in this equation is 1,100 newtons, and our normal force hasn't changed. It is 4,415 newtons. Notice that newtons cancels with newtons, and we get a dimensionless quantity, which is what the coefficient actually is. Just 1,100 divided by 4.5, which is 0.25. And that makes sense because the coefficient of kinetic friction should be smaller than the coefficient of static friction. And static friction up here is 0.35, and we got 0.25. All right, so the question is, why did I not make gravity negative here? So the force of gravity is a vector, right? Vector, just like the normal. But what I did was, because I made up to be positive, a vector which has a direction and a magnitude, I put the direction right here with this negative in front of this, which is the magnitude. So that's the magnitude. and this is the direction. So we have our negative direction for our vector of force of gravity, and we have our magnitude. So down here, what I'm doing here is I'm calculating that magnitude. This is just the magnitude. So I shouldn't be putting in negatives inside the magnitude. Otherwise, what I would be doing if I did do that was essentially throw a negative inside here, which would pop out and change the direction to positive. It would make gravity up. Okay, so we have to be very careful when we take vectors and we pull out a direction. Right? Notice that I never put vector signs on these ones. It's because I already pulled out their direction and I labeled it as a sign in front of each. Meaning that this is now just a scalar quantity because it's just the magnitude. If you like, we could even write it like so. We can put vector signs and then absolute values in front of them like this. Because we pulled the direction quantity out in front. Okay, question 2. Here we have a 2 kilogram piece of lubricated steel being pulled across a steel desk with an applied force of 3.2 newtons. If the coefficient of kinetic friction is 0.12, find the acceleration of the block. So now notice this problem doesn't have parts A, B, C, D, but we still have to do all those parts. It's going straight to find the acceleration. Okay? First step, free body diagram. So we draw a free body diagram. This is our lubricated steel on a desk. So we are going to have a force of gravity pulling down on it. We are going to have a normal force from the desk. And it's being pulled. So let's have an applied force pulling it. Or you can have tension. It doesn't really matter what you label it. And there is going to be kinetic friction opposing that motion. So there's our free body diagram. Now it says find the acceleration. So in this case, you have to decide. Should I analyze our horizontal component or our vertical component? I'm assuming it's going to accelerate horizontally. It's not being taken off from the desk. So let's look at net force in our x direction, which will equal mass times our acceleration in x, which is the acceleration we're looking for. All right, so how many forces are there in x? Well, we have 2. Kinetic friction and applied force. So what I'll do is I will say this is our positive direction. And so I'll pull the direction quantities out of that. So we have applied, right, forward minus kinetic forward instead of plus backwards equals mass times acceleration. All right, and applied force we know, 3.2 newtons, but I don't know kinetic friction. I know the coefficient. All right, so I can rewrite that using the equation we learned today, mu k f n, which equals ma. Okay, but here's another roadblock. I don't know the normal force either. But this is where you can do what we did before, right up here. Since there's only 2 vectors in our vertical direction, and since there's no acceleration in our vertical direction, if you like, I can do exactly what I did up there and write it out by going F net in y equals mass times acceleration in y. But acceleration in y is 0. It's not lifting off the desk. It's just being pulled horizontally. So if that net force equals 0, I can do the exact same I did up here. Normal minus gravity equals 0, and therefore normal equals gravity. And therefore, since the normal force equals gravity, I can write the normal force is just mass, or the magnitude of the normal force anyways, is just mass times that gravitational field strength, 9.8. So I can rewrite this as Fa minus mu k, where Fn is mg, equals mass times acceleration. Since I'm solving for acceleration, divide both sides, or every term, however you want to do it, by m, and we can solve for a. So a will equal our applied force, which is 3.2, minus coefficient, which is 0.12, times the mass, which is 2.0 kilograms, times gravity, which is 9.81 newtons per kilogram, all divided by the mass, which is 2 kilograms. Okay, so that gives us an acceleration of 0.42 meters per second squared, and I can just say